Hi, in this video I am going to solve the second set of problems related to lecture 19. Below this video you can find the link to the PDF file of these problems as well as links to these lecture notes that you currently see on your display, both in PDF and GoodNotes formats. Okay, so let us start with the first problem. Okay, in this problem A, there are several parts. The first part, we're supposed to simplify this fraction that you can see here. So if you remember, if I want to simplify a rational expression, I need to factorize the numerator and the denominator separately and try to find the common terms between the numerator and the denominator, common factors, and then simplify them. Yes. So because this seems a little bit long problem, so I will do the numerator and the denominator separately. Okay. So I would write the numerator is equal to. So here, if you see what I can do, this is a complete square because this expression is raised to power 2, and clearly that this is also a complete square. It's 2bx to power 2. So for the numerator I can use the conjugate pattern to factorize this expression. So then it becomes a squared x plus 1 plus b squared x minus 1, and then I will have this minus the square root of the other one, which is 2abx, and then I will have the same expression added together. Yes, expressions added, so it becomes this plus 2abx. Yes, so this expression is the square root of the first one, and this expression is the square root of the second one. The square root of the first one minus the square root of the second one, the square root of the first one plus the square root of the second one. Okay, but let me continue. So let us see how it goes. Then here, what I can see, I multiply this here and I will multiply this here, the same for these two pair of brackets. Okay, so then it becomes a squared x plus a squared. Then I will have b squared x minus b squared, and then finally I will have minus 2abx. And the same thing for the next pair of brackets. I multiply it inside. Yes, plus 2abx. Now between this term and this term and this term I can factor a x out. The same is here, this one and this one, this one. So then it becomes equal to a squared plus b squared minus 2ab multiplied by x. I am left with a squared minus b squared. So let me explain it again. So between these three terms, I factored x out. From this term, a squared is left. From this term, b squared is left. And from this term, minus 2ab is left. And then you see that there is an a squared here and a minus b squared here, which I wrote them at the end. So the same explanations here. So let me write for the second one. I can do exactly the same thing. So I factor an x out between these underlined terms. And then I can write a squared minus b squared again. But now what can I do here? I can collect these terms into a quadratic term. It's a minus b to power 2, and I can write this as a plus b to power 2, and in both of them this can be factorized as a minus b times a plus b, both here and here. Okay, so this becomes a minus b to power 2x plus a minus b times a plus b, and then the same thing for the other pair of brackets. Yes? And now you can see that this a minus b here and here is a common factor. And in this pair of brackets, this a plus b here and here is a common factor. So from the first pair, I can factor a minus b out. then I will be left with 1 minus AB times x, and then plus A plus B. And from the second pair of brackets, I can factor A plus B out. Then I am left with A plus BX plus A minus B. So let me just repeat it again. So you see, A minus B, I pulled A minus B out from here and here. I had two factors of A minus B, so one of them is left, and because A minus B is pulled out, only A plus B is left. And the same here. But what can I do now? I can see that this is equal to A minus B. Let me write it in a more proper way. So A minus B, A plus B, and then I can also multiply this here and also expand this here. So it becomes AX minus BX plus A plus B, and then I will have AX plus BX plus A minus B. Okay, so this is a factorization of the numerator. So I got four factors: A minus B, A plus B, and this expression and that expression. Now let me go to the denominator. The denominator is equal to, again, I have the complete square here minus another complete square. So again, I can use the conjugate rule, yes? So what can I do? I can write it as ax plus 1, the square root of the first one, minus the square root of the second one, multiplied by the square root of the first one plus the square root of the second one. But I can simplify this a little bit, each factors individually. So here I multiply this expression in, I multiply in this, and I also expand this, and I also expand that. So what I get is ax plus a minus bx plus b, and on the second one I will get ax plus a plus bx minus b. Yes? And then I really don't need to go further, because if you see, this factor that appears here is exactly one of these factors. Yes? ax is ax, minus bx is minus bx, and then I have positive a, positive b. Here I also have positive a, positive b. And the same thing here. This is exactly this expression. So my question mark now is the division of the numerator by the denominator. So yes, so the numerator, say, divided by the denominator. What happens? This becomes equal to these. When I divide, this factor will cancel that factor, and this factor will be cancelled by that one. What is left for me is just a minus b times a plus b. And now this, we cannot simplify it more. I prefer to multiply it back. So using the conjugate pattern, the answer becomes a squared minus b squared. And that's exactly the answer provided in the problem set. Okay, now we solve the second part of this problem. We are supposed to simplify this expression. As before, so I start simplifying the numerator, factorizing the numerator and the denominator separately. So let me write n for the numerator. This is equal to, in the numerator I can take this one and with this one, then they become the difference between two complete squares, and I can take this one with that one. Again, they become the difference between two complete squares. So in both cases I can use the conjugate rule, yes, to factorize it. So the first part becomes the square root of the first one, x plus a, minus the square root of the second one, y plus a, and then multiplied by square root of the first one, x plus a, plus the square root of the second one. Okay, and then plus, I can do the same thing between this one and that one. So it becomes x plus b, square root of the first one, minus the square root of the second one, multiplied by square root of the first one plus the square root of the second one. Yes? Okay, now let us simplify these expressions a little bit more. So here I open these brackets, the same here, and here. So then it becomes x plus a minus y minus a. The next one becomes x plus a plus y plus a. And then I have plus the same thing for the next pair of brackets, x plus b minus y minus b, and then finally x plus b plus y plus b. Yes, and now you see that this a and this a are gone. Here the a's are added together. Here these two b's are gone. Here these two b's are added together. So then it becomes x minus y, x plus y plus 2a, and then I will have plus x minus y, and then I have x plus y plus 2b. So that was quite successful because now I can see that I have a common factor that emerges, and I can factor this common factor out. So this becomes equal to x minus y. From the first one, x plus y plus 2a is left. From the second one, x plus y plus 2b is left. And I can collect the terms a little bit more here. X and x2x, y and y2y. So it becomes x plus 2x plus 2y, and I have 2a plus 2b. And of course I can also factor 2 out if necessary. So x minus y times x plus y plus a plus b. So that is the factorization of my numerator. For the denominator, so let me call it d. So in the denominator, it seems that we cannot do anything special, so the only thing we can do, we expand this one and hope for the best that they can be simplified, and then I can write it in the factorized form. Okay, so let us do that. I expand the first one, so I multiply these two. I also multiply these two, but I can use the common common term identity. So the expansion of the first one is x squared plus a plus bx plus ab, and the next one I have a negative sign in between, so it becomes y squared plus a plus b y plus ab. Yes, so I have multiplied these and written it in this form. Now I open this bigger pair of brackets, so it becomes x squared plus a plus b x plus ab, and then it becomes minus y squared minus a plus b y minus ab. Now you see that this ab and that ab cancel each other, and between these I can group these two together. So let me underline them. I group this one, so this AB and that AB are gone. I underline these two, and I underline these two. Yes, so then I can continue in this way. So it becomes x minus y times x plus y. What I have written here is the factorization of x squared minus y squared, and between these two terms you see that a plus b is a common factor, and I can pull it out. So it becomes a plus b times x minus y. This is a good news because now you see x minus y again emerges, and I can factor it out. So it becomes x minus y, and then what is left from the first one is x plus y, and what is left from the second one is just simply a plus b. And then what you see is that what appears in the denominator is exactly half of what appears in the numerator. So if I want to answer the question mark here, the numerator divided by the denominator, you see that this factor cancel that factor, this factor will cancel that factor, so what is left for me is just simply 2. So this expression is equal to 2. But of course this is equal to 2 except for those values of x, y, and a and b where the denominator becomes 0. So this expression is always equal to 2 except for those values of the parameters x, a, and y, and b for which the denominator is equal to 0. But here usually in the simplification we always assume that this is the case and the denominators are defined. Okay? Okay, now let us solve problem number 3. So here we are supposed to simplify this expression. So I factorize the numerator and denominator separately, as I have done so far. So the numerator is a trinomial, and it contains two complete squares. X to the 4 is the complete square because it's the square of the x squared, and 1681 is also a complete square because this is 41 squared. But unfortunately this doesn't follow a quadratic rule. Why? Because if I take the square root of this one, it gives me x2. If I take the square root of this one, it gives me 41. And if I multiply it by 2, it gives me 82x squared. And 82x squared is not the middle term, so it's not a quadratic rule. But I can actually, instead of this, I can write 82x squared to make a complete square out of it. But I need to subtract minus 169x squared from it. What I mean is that, let me just tell you, let me copy and paste the numerator. The numerator is x to the 4 minus 87x squared plus 1681. Here I can write it as x to the 4. Instead of minus 87x squared, I write positive 82x squared. The goal is to make these three make a quadratic pattern, but of course I need to make it right. Yes, I have negative 87, but I have written positive 82. So what I can do, I can subtract 169x squared. Yes, and then it becomes exactly equal. So x4 is x4, 1681 is 1681, and then this positive 82x squared minus 169x squared becomes exactly minus 87x squared. So what I have done is completely legitimate. Now the first three gives me the quadratic rule, so it becomes x squared plus 41 to power 2, and instead of minus 169x squared I can write 13x to power 2, because we know that 13 to power 2 is 169. And now probably you realize what was the benefit of doing that, because now I have the difference of two complete squares and I can use the conjugate pattern. So it becomes the square root of the first one minus the square root of the second one multiplied by square root of the first one plus the square root of the second one. But I prefer to write it in a more organized way, so I write x squared first minus 13x second and then 41, and then the other one is x squared plus 13x plus 41. Yes, so that is the numerator. Now let us go to the denominator. So for the denominator, if you have watched the videos for factorization, you have enough experience to know what to do. So I take this one and multiply it by this one, and I will take these two and multiply them together, and then when I found the answers I will multiply them again, and then of course I have to add 1 at the end. So let us do that. So here I am writing this, I am multiplying this by this, I am using the common term identity. So the common term should be squared, so this becomes x squared. Then I need to add these two terms, which becomes 13, and multiply it by the common term, so it becomes positive 13x. And then finally I have to multiply these two numbers, which becomes 40. What I have written here is the product between these two. I do the same thing for this product, so it means that I need to raise the common term to the power of 2. Then I need to add these two numbers, which becomes exactly 13, and that was the reason that I took these two together and these two together. So it gives me 13x again. And then of course I need to multiply 6 by 7, it becomes 42. So now you realize why this was better, because now this expression is in common between these two pair of brackets, so it means that this can play the role of the common term. So then if I want, by the way, I have forgotten, I have a 1 at the end, so let me write plus 1. Now I give the role I give the role of the common denominator to this, so it becomes the common term to this, and it becomes common term squared, x squared plus 13x to power 2. And then I have these two terms added together and multiplied by the common term. So if I add this one and that one, it becomes 82. So it becomes 82 and multiplied by the common term, which is this one. And then finally, what I do, I have to multiply these two numbers together. So it becomes 40 times, let me write it, 40 times 42, yes? And what I have is a plus 1 at the end. Okay, so if I multiply this 40 times 42, it becomes 1680, and then I have a 1 at the end, you see? So this becomes exactly a complete square again. Yes, so that is very nice. This is exactly the term that I need to make it a complete square. So if I take this a box, this is still a box, so it becomes box to the 2 plus 82 box, and then I have a 41 to power 2, because 1681 is 41 to power 2. And then you realize that this is a quadratic pattern again. Yes, so what I can do, I can write it as x squared plus 13x plus 41 to power 2. Let us double check. If I ask you to raise, this expression to power 2, you would say that this is my first term, so I square it, so that's correct. And then you would say 2 times the first one times the second one, which will give me this one. And finally you would say 41 to power 2, which gives me 1681. But of course, I don't need these pair of brackets anymore here, so let me remove them. So then it becomes x squared plus 13x plus 41 to power 2. Okay, and now I want to answer the question mark. This question mark is the numerator divided by the denominator. And then what you see is that in the denominator, I have 2 factors of this. But in the numerator, I have 1 factor of that exactly, but there is another factor which is not this one. So it means that this, one of these factors and that one are totally gone. So what is left in the numerator is this one, and what is left in the denominator is one of these factors. So then this cannot be simplified more, yeah? So it becomes x squared minus 13x plus 41 divided by x squared plus 13x plus 41. And as I told you before, you can see that this cannot be factorized anymore in the set of rational numbers. So that is the end of this problem. Okay. Okay, now next part, number 4. We are supposed to simplify this. Again, I simplify the numerator and the denominator separately. So the numerator, I want to see what can I do for the numerator. What I want to do is I want to write the denominator as a quadratic function in x. So if that's the case, I can write it in this form. So x squared minus 2b as the factor of x, and then the rest of it I can just open it, yes? It becomes minus 4a squared, and then I multiply minus 4a by minus 2b, it becomes positive 8ab, and then finally I have minus 3b squared. Okay, so if you want, I can write it as in a pair of brackets and put a positive sign here. So what I'm saying is that you can compare this expression with ax squared plus bx plus c, where a is 1, b is minus 2 little b, and capital C is this expression. So of course there might be different tricks, but I think the first thing comes to mind for this expression is to use the trick of the general trick for factoring the quadratic polynomial. So namely, first I calculate delta of this expression. So delta is equal to this expression to power 2, so it becomes 4b squared, then minus 4 times a, which is 1, multiplied by c, which is this expression, so it becomes minus 4 times minus 4a squared plus 8ab minus 3b squared. Yes? But now you see that there is a 4 in common in these two. I can factor that 4 out. From the first one, b squared is left. From the second one, a negative sign, negative 1 is left, so that I multiply it here, here, and here. And I remove the pair of brackets. So it becomes positive 4a squared minus 8ab, and then finally positive 3b squared. But then it can be simplified a bit more. So this b squared and that 3b squared can be combined. So I will get 4a squared minus 8ab, and then I will have 4b squared. So again, I can pull out a factor of 4, so it becomes 16a squared minus 2ab plus b squared. But then this is very known pattern for us. This is just a minus b to power 2. So now I will find the roots, yes, the roots of this polynomial. So what are the roots? So the roots are x is equal to minus b, so minus this coefficient, which is 2b, plus or minus a square root of your delta. But the good point is that my delta itself is a complete square, so when I take the square root of that, the square root of 16 becomes 4, and the square root of a minus b to power 2 is a minus b, and then I divide this expression by 2 times the coefficient of x squared, which is 1, so it becomes 2. Let me fix this one, it has been accidentally erased. Okay. Now you can see what I can do. I can factor a 2 out again. So then I am left with b plus or minus 2a minus b divided by 2. And then this factor of 2 and that factor of 2 are cancelled, so I will get two answers, b plus or minus 2a minus b. So I will have two answers. I will take care, so let me call it x1. I will first consider the positive one, so then it becomes 2a minus 2b plus b, which becomes minus b, and x2 becomes b minus 2a minus b, so the answer becomes minus 2a plus 3b. And then it means that the numerator can be factorized in this form. So the numerator is equal a, which is this number, so I don't need to write it here. I open two pair of brackets and I would write, so do you remember the formula was a times x minus x1 times x minus x2. x1 and x2 are the roots of the polynomial, second degree polynomial, and a is the coefficient of x squared. So if I want to use that formula, I would write x minus x1, I will take this for x1, and x minus x2, which is this one. And then I will remove the inner pair of brackets. So then it becomes equal to x minus 2a plus b, and then x plus 2a minus 3b. So that would be what I get for the numerator. And for the denominator, I can use the same trick. So what is my denominator? The denominator is again a quadratic polynomial. So let me write it more clearly here. So let me just copy and paste this again. So this is x squared minus 4ax plus 4a squared minus b squared. Let me use the same trick, even though you can probably do it in a different ways. But let me just use the same trick. So let me calculate delta for this. So delta is this expression to power 2, so it becomes 16a squared, minus 4 times a, which is 1 in this case, times this expression, which is playing the role of c, which becomes 4a squared minus b squared, and then this becomes equal to 16 a squared minus, if I multiply it becomes 16a squared plus 4b squared, and these two 16a squareds are cancelled, so I am getting 4b squared. And again, the good point is that this is a complete square. So now if I want to find the roots of this, it becomes negative the coefficient of x, which becomes 4a. I'm using ABC formula, and then this becomes a square root of my delta. Yes, but my delta is so simple that I can do it in my head. The square root of this is 2b, and then I divide this by 2 times the a coefficient of x squared, which is 2. So if I factor a 2 out, it becomes 2a plus or minus b divided by 2, so I will get 2a plus or minus b. So for example, x1 in this case I can consider to be 2a plus b, and x2 in this case I can consider it to be 2a minus b. And then again, the denominator, if I want to write it, it becomes equal to, I put 2 x's here and there because the coefficient of x squared is still 1, so in principle I should write 1 here, but that's not important. X minus x1, which becomes x minus 2a minus 2b, because this minus sign goes for this one and that one, and the second one minus sign goes for this, it becomes minus 2a, minus sign goes for this, it becomes positive b. So it becomes minus 2a positive b. So in the denominator I have these two factors, and in the numerator I have these two factors. And then you see that again only one factor is in common. This factor appears here and there, so when I divide them this is gone. But these two factors cannot be simplified anymore. So the question mark is actually the numerator divided by the denominator, which is equal to x plus 2a minus 3b, that's the factor left from the numerator, and the denominator is x minus 2a minus b. But what I have answered this in the answer sheet, but I have multiplied this numerator and the denominator by a negative sign, so this becomes 3b positive, negative 2a, negative x, and in the denominator it becomes positive b, positive 2a, and negative x. But of course, the reason that I did it here because I wanted to get the exact answer that I already provided for you, but this is completely valid if you stop here. Okay? Okay, now we are going to solve this problem. Again, I factorize the numerator and the denominator separately, and I want to use the same trick that I used in the previous problem by looking, for example, you see the numerator here can also be considered as a quadratic polynomial in x, but now because I have two terms involving x, so I need to factorize and arrange the terms. Okay, so what I will do for the numerator, I would write it in slightly different way, but my goal is to write it as a quadratic polynomial in x. So between this term and that term I can factor a minus x out, so I put the minus sign here, I put my x here, and then if I take minus x out from here, y squared is left, positive y squared is left, and if I put minus x out, so positive z is left. This would be the coefficient of x, and then I would write all the leftovers. Yes, so let me write with positive 1, which is 5y squared z minus 2y to the 4 minus 2z squared. Yes, and now what I have written here, you can compare it with ax squared plus bx plus c. A in this problem is 1, b in this problem is this minus y squared plus z, and c in this problem is the whole expression here. And I use the same trick that I did before. Yes, that's the simplest possible case usually. So I calculate delta. Delta is this number to this expression to power 2. The negative sign is gone, so I am left with y squared plus z to power 2 minus 4 times the first coefficient multiplied by this expression. So it becomes 5y squared z minus 2y to the 4 minus 2z squared. And then I try to simplify this expression. I use the quadratic rule to raise this to power 2, so it becomes y to the 4, 2 times the first one times the second one, and then the second one to the 2. And then I multiply minus 4 inside, so it gives me minus 20 y squared z, positive 8 y to the 4, and finally positive 8z squared. And then you see that this y to the 4 and 8y to the 4 gives me 9y to the 4, and then I will have this term 2y squared z minus 20y squared z gives me minus 18y squared z, and finally I will have this z squared plus 8z squared. It gives me 9z squared. Then I can factor a 9 out. It becomes y to the 4 minus 2y squared z, and then I have z squared at the end. But hopefully you immediately realize that this is a quadratic pattern on its own, so this becomes 9 times y squared minus z to power 2. Yes, because the first one to the 2 gives me y to the 4. 2 times the first one times the second one with the negative sign will give me exactly this middle term, and then the second one to the 2 is this one. So what I have written is completely correct, and the good point is again that this delta is a complete square. So now I need to find the roots. So x is equal to minus b, but this will play the role of the b, so minus b becomes positive of this expression, and then plus or minus a square root of delta, but delta is a complete square. If I take the square root of 9, it becomes 3, and then the square root will cancel this power of 2, so it becomes 3 times y squared minus z, and then I divide this by 2 times the coefficient of x, which is 2 times 1. And then I will have two roots. One I call this x1. I consider the positive sign z, y squared plus z plus 3y squared minus 3z, and then I divide this by 2, then it becomes 4y squared and then minus 2z divided by 2. So I factor a 2 out and I cancel the 2's, so what is left for me is just this expression. And then I will do the same thing here for x squared, sorry, x sub 2, the second root, by taking the negative sign into account. So this becomes z minus 3y squared plus positive 3z divided by 2. If I simplify that, it becomes 4z minus 2y squared divided by 2. If I factor a 2 and the 2 cancel, I will be left with 2z minus y squared. So the numerator is now equal to, so it becomes x minus the first root, so minus this becomes positive z negative 2z squared, so it becomes negative 2y squared positive z, and x minus the other root, so this becomes positive y squared minus 2z, positive y squared minus 2z. So that is the expression that I get for the denominator. So for the numerator. Now for the denominator, I want to do the same thing. Yes, this is already a polynomial in x, a second degree polynomial in x, but let me write them in more organized way. So I would write x squared, but instead of writing this middle term in this way, because I want to consider x as the variable, I would write it as minus 3y squared, and then multiplied by x, and then the rest of it I can put a pair of brackets around them to emphasize that I want to consider this as just one single term. Okay, and then I do the same thing as before. So I calculate delta. Delta is this number to power 2, which gives me 9y to the 4 minus 4 times the first one times the last one, which gives me this expression. And now I write it as 9y to the 4 minus 8y to the 4 minus 4y squared z positive 4z squared. And if I simplify this a little bit more, so here this gives me only y to the 4. The middle term is minus 4y squared z, and finally the last term is 4z squared. But again, hopefully you can recognize the quadratic pattern here. This becomes y squared minus 2z to power 2. Why is that? Because if I raise this to power 2, the first one to the 2 gives me exactly this. 2 times the first one times the second one will give me exactly this. And finally the second one to power 2 is exactly this. Okay, now I can factorize my new denominator. So therefore the denominator becomes equal to I have to calculate the roots first. So x becomes equal to negative b. This is my b, so negative b becomes positive 3y squared, then plus or minus square root of delta. So square root of delta will cancel this power of 2, then I will get y squared minus 2z. Then I have to divide it by 2 times a, which is 2. And then I will have two roots again. So one of them is x1 is equal to, consider the positive sign. Yes, it becomes this, and then it becomes 4y squared minus 2z divided by 2. I factor a 2 out, and the denominator will cancel out, so I will have this expression. And now for the other root, I can write x2 and consider the negative sign. So it becomes 3y squared minus y squared, but plus 2z divided by 2. And then it becomes 2y squared plus 2z divided by 2. And then I can factor a 2 out and simplify it. It becomes y squared plus z. Now I can write the denominator is equal to x minus the first root, which becomes minus 2y squared plus z. I multiply this by a negative sign here and there, and then x minus the other root, which becomes minus y squared minus z. Now you see, this is your numerator and this is your denominator. You're supposed to divide numerator and denominator. You can immediately see that this factor is exactly in common, so they will cancel out. But these two factors are not the same, so what is my question mark now is equal to what is left for me is x plus y squared minus 2z, and then I divide this by x minus y squared minus z. And that is the answer to this problem. Okay? Okay, now let us simplify this fraction. The numerator of this fraction, even though it's a third-degree polynomial, but it is not hard to recognize that you can factor it easily. So you really don't need to go and find the factors. If you remember, in principle, if I want to factorize a polynomial like this, I have my hopes on finding the factors of this and then hoping that one of those integer factors is a root of this polynomial, and then use the long division method to factorize the polynomial. Even though that's also possible here, but it is very easy to see that if I take these two and then take a minus sign out from here, I will exactly have my common factor that I am looking for. So what I write for n is I take this one with that one, I will take these two together, so I can write it in this form. I can factor a 4x squared out from the first two terms, then I am left with x minus 2, and from the second and the fourth from the second group I can take a minus sign out, it gives me x minus 2, and then I can take x minus 2 out, it gives me 4x squared minus 1, and then 4x squared minus 1 is actually a conjugate pattern, so I can write it as x minus 2, 2x minus 1, and 2x plus 1. Very simple, okay? But the denominator is a little bit more tricky. So what should I do? It's not that easy to guess what we're supposed to do. So what I do first, I hope that there are some integer roots for this. And then it's clear that negative numbers cannot be roots, because if I choose a negative number for x, then it becomes positive, this becomes positive, and these are already positive. The sum of some positive numbers, a bunch of positive numbers, cannot be equal to 0. So I have factors here, plus or minus 1, plus or minus 2, plus or minus 4. I will not consider the negative ones because negative ones will not work. So I need to check 1, 2, and 4. It's very easy to see that 1 doesn't work either, but if you check, it will work for 2. If you check 2, it will work. So put 2 here. It becomes 4 times 16 minus 20 times 8 plus 33 times 4 and minus 20 times 4, minus 20 times 2 and then plus 4. If you calculate this, this becomes indeed equal to 0. So what does it mean? This means that this polynomial is divisible by x minus 2. Okay, so let me write for the denominator. So for the denominator, I use the long division method. So I would divide this expression. I realize by checking that 2 is a root of this polynomial. So I will divide this polynomial by x minus 2. Okay, so if I do the long division, so let me change my color. So I don't repeat how should I do that. If you have forgotten, you can go back and watch one of the previous videos that I was discussing about factoring polynomials using the long division method. So I divide the first term by the first term, and so it becomes 4x to the 3, and then I multiply it here and put them with the opposite signs here, so it becomes minus x 4x to the 4, and the next one becomes positive 8x to the 3. Yes, and then what I do, I add them. This one and that one are gone, so I will get minus 12x to the 3, and then I will bring the other terms down. Yes, and then I will continue the process. So the next one would be minus 12x squared. So it becomes positive 12x3, and then it becomes minus 24x squared. Yes, and then again I add them. So this one and that one are gone. I will get 9x squared minus 20x plus 4, and the next one would be 9x. So it becomes minus 9x squared positive 18x, and then again I add them. This becomes negative 2x plus 4, and finally I would write minus 2, becomes positive 2x minus 4, and the remainder, as we expect, becomes 0. So this implies that the numerator is equal to x minus 2 times this quotient, which is 4x to the 3 minus 12x squared plus 9x minus 2. Okay, but it might be the case. First of all, you see that sorry, this is denominator, not numerator. So this is my denominator is equal to this. Okay, and then for the time being, as you see that there is a factor x minus 2 and x minus 2 that can be cancelled, but there is no guarantee that this cannot be simplified anymore. So let us see that if we can factorize this polynomial once more. Okay, so again, we hope that this polynomial will have an integer root, but if that is the case, the integer roots are among the factors of minus 2. So these are plus or minus 1, plus or minus 2. Okay, but you can immediately see that, for example, negative values does not work. Because if I put a negative value for x, this becomes negative, this becomes negative, and these are already negative values, so it becomes negative, and it is not 0. So I need to choose positive numbers. So there are two choices for me left, 1 and 2. And then I have already done that, so if you put 2, then it becomes 0. So this means that this polynomial on its own is also divisible by x minus 2. So if that's hard for us to factorize this by breaking the terms, which is usually hard, I can just rely on my skills in doing long division. Okay, what that long division should be is I need to divide 4x to the 3 minus 12x squared plus 9x minus 2 with x minus 2 once more. Yes. So I put x minus 2 here. Let me change my color here again, so it becomes 4x to the 2. I multiply it here and change the signs and put the numbers here. So it becomes minus 4x cubed plus 8x squared. Then I will be left, this one and that one are gone. I will get minus 4x squared, and I will bring down all the other terms. And then what I do, it becomes minus 4x, it becomes positive 4x squared and negative 8x. Then if I do it again, it becomes just simply x minus 2, and then I will have a 1 here. It becomes minus x plus 2, and as I expect, the remainder becomes 0. So what does this mean? This means that this polynomial itself is a product of this and that expression. Yes, so this means that therefore, so let me change my color. So therefore, 4x to the 3 minus 12x squared plus 9x minus 2 is equal to x minus 2 times 4x squared minus 4x plus 1. But hopefully you can also immediately recognize that this is a quadratic rule. So this can be written as x minus 2, 2x minus 1 to power 2. Yes? Because then the first one to power 2 gives me 4x squared. 2 times the first one times the second one will give me the middle term, and this one to power 2 gives me the positive 1. Okay, but this part is this expression. I plug this back here, and there is another x minus 2 which will be multiplied by here. So finally, hence, the denominator that I am looking for is equal to x minus 2 to power 2. Let me write it with black. X minus 2 x minus 2 to power 2, 2x minus 1 to power 2. Yes, so this expression is this. I have to multiply it by another x minus 2, so it becomes x minus 2 to the 2 and 2x minus 1 to the 2. Okay, and now everything is okay, so I can make it a little bit smaller so that you can see it. The question mark that I want to answer is of course the numerator divided by the denominator, which becomes equal to, the numerator is x minus 2, 2x minus 1, and 2x plus 1. I am supposed to divide this by x minus 2 to power 2 and 2x minus 1 to power 2. Yes, so what can I do? This one and this one of these are cancelled. This one and one of these are cancelled. So what is left for me in the numerator is just simply 2x plus 1, but what is left for me in the denominator is x minus 2, 2x minus 1. But of course I can I can multiply this back at the end if there is no hope that I can simplify. So I can write 2x plus 1 in the numerator. If I multiply this by this, it gives me 2x squared. And now if I multiply this by that, it gives me minus x. Multiply this by this gives me minus 4x. So minus x minus 4x is minus 5x. And finally minus 2 times minus 1 is positive 2. And that is the answer which has been provided in the answers part of the PDF file. Okay? Okay, now let us start number 7. Here, if you look here, both the numerator and the denominator are symmetric polynomials in A and B. Yes, what I mean by symmetric, if you remember from the last session for factoring polynomials, a polynomial is said to be symmetric if interchange between A and B doesn't change the polynomial. So you see, if I change A to B and B to A, nothing will change here, nothing will change here, nothing will change here. So the numerator is a symmetric polynomial, and the denominator for the same reason is a symmetric polynomial. And if you remember, we have elementary symmetric polynomials in two variables. If you don't remember, you can go and see that video, the last video for factoring polynomials. We introduced two elementary symmetric polynomials. One of them we call it E1. E1 is A plus B, and the other one is E2, which is the product of A and B. And then I proved a theorem there that any symmetric polynomials in two variables can be written as a polynomial in terms of E1 and E2. Okay, so sometimes it will help us if I write a symmetric polynomial in terms of these two polynomials, and then make it simpler. It makes it simpler to factorize the polynomial. Okay, so let me start the numerator. Yes, so the numerator. Okay, so here, if you remember, we had an identity that I proved when I was doing algebraic identities in previous lectures. The identity was a plus b to power 3 and then minus 3ab times a plus b. And then now you see that a plus b, we called it e1, and a times b, we called it e2. So I can replace these things here, so it becomes e1 to the 3 minus 3e2 times e1. Yes? So it means that the numerator n can be written in this form. Instead of this expression, I can write this. This is just e1, so it wants e1 to power 3, and 2a3b3 can be assumed as 2 times ab to power 3, but ab is just e2. So this becomes 2e2 to power 3. So I replace everything, so it becomes e1 to power 3 minus 3, let me write them in order, e1 times e2, and then multiply it by e1 to power 3, and finally plus 2 times e2 to power 3. Now let me simplify this. I expand that, so it becomes e1 to power 6 minus 3 e1 to power 4 e2, and then I will have plus 2e2 to power 3. Based on the experience that you have got so far, I don't think it's hard to guess that you can break the middle term. It will help you to have the common factor at the end. So I would write it as e1 to power 6 minus e1 to power 4 e2, and then minus 2e1 to power 4 e2, and then finally at the end I will have 2e2 to power 3. Yes. Okay, so if I want to explain what I have done, these two terms will give me this term back. Yes? Okay, so what I have done, I have broken this term into two terms, into the sum of the two terms. And then why this is good, because you can immediately realize if I group these two together, and if I group these two together and factor them separately, then a common factor will emerge. Okay, so from the first group I can pull out an e1 to the 4, so the answer becomes e1 to the 4, and what is left for me is e1 to the 2 minus e2. And from the second pair I can pull out negative 2e2. Yes, so I pull out negative 2e2, and then what is left for me in the first one is positive e1 to power 4 but negative e2 to power 2. But then the second one is a conjugate pattern, so I can factor it more, so it becomes e1 to 4, e1 to power 2 minus e2 minus 2e2, then I will have e1 to power 2 minus e2, e1 to power 2 plus e2. Yes, so I factorize this part using the conjugate pattern. The good point is that now this factor which emerges is a common factor, and I can pull it out again, so it gives me a factorization of the numerator, at least a factorization, even if it might be not complete. Okay, so then I will have e1 to power 4 from the first one minus 2e2 times the second one. Yes, so let me explain. So I pulled this factor out. What is left from the first one is e1 to the 4. Because this has been pulled out, so minus 2e2 and e1 to the 2 plus e2 are left. But I can multiply this inside, so then it means that my numerator, so let me write it at the end, so the numerator is equal to e1 to power 2 minus e2, and then I will have e1 to power 4 minus 2e2, e1 to power 2 minus 2e2 to power 2. Yes, so I can put this in a box for future reference. And now I go to the denominator. Denominator also is the same story but simpler. So here that's also a symmetric polynomial, so let me write the denominator. So my denominator d is equal to, if you remember, we had this formula that a squared plus b squared, I think it is in the first lecture on algebraic identities part 1, that this becomes a plus b to power 2 minus 2ab, and then e1 is a plus b and e2 is ab, so you can write it as e1 to power 2 minus 2e2. And then of course this is just e1, so it becomes e1 to power 2, and this is nothing except e2 to the 2. So if I write everything, it becomes e1 to power 2 minus 2e2 multiplied by e1 to the 2 plus e2 to the 2. Yes, so what I do, I multiply this again, so it becomes e1 to the 4 minus 2e2 e1 to the 2 plus e2 to the 2. Okay, and then hopefully you immediately realize this is a quadratic pattern. Yes, so I can write it as e1 to the 2 minus e2 to the 2. Yes, why? Because the first one to power 2 gives me this. 2 times the first one times the second one with negative sign will give me exactly this, and finally this to power 2 gives me the last one. So the denominator is actually very simple, so let me write it for the future reference, that d is equal to e1 to the 2 minus e2 totally to power 2. So that is d. Now what I want to see, you see that there is a common factor here between the numerator and the denominator. So the question mark that I am looking for, which is the numerator divided by the denominator, is simply this expression that I can simplify those. Yes, so what is left for me in the numerator? e1 to the 4 minus 2e2 e1 to the 2 minus 2e2, and then what is left for me in the denominator is only one factor of this expression. So hopefully you realize what's going on. This is my numerator. If I divide it by the denominator, I have one of these factors which will cancel one of these factors. So this expression is left in the numerator, and then one of these factors is left in the denominator. Okay, so then I need to substitute back. At least I were able to simplify this expression. So if I substitute things back for the denominator, it's very simple. Instead of E1, I plug a plus b back minus E2, which becomes ab. And for the numerator, it becomes a plus b to the 4 minus 2ab times a plus b to the 2 minus 2ab. Okay. Of course, I have to simplify, so I cannot just stop there. For the denominator, I don't have any problem. So the denominator becomes a squared plus 2ab plus b squared, but minus ab and 2ab will be simplified to ab. So what is left for me in the denominator would be exactly this expression, which is given in the answers. Okay. But of course I can do the same thing for here, but to avoid raising it to power 4, even though we know how to raise it to power 2, to power 4, I told you how to do it using the binomial expansion, for example, or you can raise it to power 2 once and then raise it to power 2 again. But to avoid that, I prefer to do it in this way. So as I told you, hopefully you realize the denominator is just a squared plus ab plus b squared. For the numerator, for making life simpler, I just factor a plus b to power 2, not because I want to factorize, because I want to make it simpler to calculate or to expand. So what is left from here is the second power of a plus b, and then I will have a minus 2ab at the end, yes, and then I have a minus 2ab left. Okay, but then this one gives me a squared plus b squared plus 2ab. That 2ab and this negative 2ab are gone, and then in the first term I raise it to power 2, so it becomes a squared plus b squared plus 2ab multiplied by, as I told you, that a squared plus b squared plus 2ab and 2ab are cancelled, so I am left with a squared plus b squared, and then I have minus 2ab. I am doing all these things to avoid direct expansion. Of course, that's up to you if you want to do it. And then, of course, I choose to multiply it in this form. I take this one expression and multiply this by one expression, so it gives me a squared plus b squared totally to power 2 plus, and then I multiply this expression by just 2ab, so it gives me 2ab times a squared plus b squared, and then finally I will have, okay, sorry, I realized that I missed something. You see here there was a power of 2 here that when I wanted to bring it down I forgot. Yes, so there is a power 2, but that's not a big problem. See, that's a power of 2. This power of 2 will give me a power of 2 here and here. This also give me a power of 2 here and here. Sorry. And then I will have minus 2a squared b squared, and the whole expression divided by a squared plus ab plus b squared. But then again, what I can do, I can raise it to power 2 in my head. This gives me a to the 4, b to the 4, but 2 times the first one times the second one will be cancelled by this term. Okay, so what is left for me is a to the 4 plus b to the 4, and then what I need to do is to multiply this here. So this becomes 2a to the 3b plus 2ab to the 3, and then I divide this expression by a squared plus ab plus b squared. So if I want to write it exactly as I have written in the answer, I have written it in this form, that this is a to the 4 plus 2a to the power of 3. I have ordered it in the descending order of the exponents of a. 2a b to the 3, and then finally b to the 4, and the denominator is a squared plus ab plus b squared. Okay, so that is the answer to this problem. Okay, now we go to the next problem. Here we know that a, b, c, x, y, and z are non-zero real numbers for which this relation holds. Based on this assumption, we want to simplify this rational expression. Okay? What motivated me for the solution that I want to present here? I actually considered these terms individually. So here, this will give you x squared y squared minus 2 times the first one times the second one. So if you look, I will have a term minus 2abxy. And for the same reason, you will have minus 2bcyz. And here you will have minus 2cazx. So that was my motivating starting point to see this solution. So what I did, I started from this assumption that ax plus by is equal plus cz is equal to 0. So to generate this 2abxy, I moved this cz to the right, so it gave me this expression minus cz, and then I raised both sides to power 2. And then I expand the left-hand side, so it gave me a squared x squared plus 2 times the first one times the second one, plus the second one to power 2, and it gives me on the right-hand side positive c squared z squared. And then what I did, because I want to have negative 2abxy here, so I move this one to the right and then move this one to the left by changing the sign. So what I get is that a squared x squared plus b squared y squared minus c squared z squared is equal to minus 2abxy. Yes? So this is one relation. Okay? And now, similarly, for the motivation is just to get minus 2bcyz. So I can just use this the other way around. So I would say I start again from this one, but instead of moving cz to the right, I will move ax to the right. So then I will get by plus cz is equal to minus ax. Then I raise both sides to power 2, something like this. And then I would write the first one to the 2 plus 2 times the first one times the second one plus the second one to the 2, and on the right hand side I will have a squared x squared, and for the same reason I write b squared y squared, I keep c squared z squared, and I move this one to the left and then this one to the right. So then it becomes minus a squared x squared is equal to minus 2bcyz. So this is also one expression that I immediately get from here. Okay, so now I don't want to repeat this. Again, similarly, this time by moving by to the right hand side and raise it to power 2, and then doing the same calculations, you will get this expression. You will get a squared x squared plus c squared z squared minus b squared y squared is equal to minus 2cazx. So it's very, very similar to these calculations, and you will get this expression. Now let me start doing the numerator now. So let me make it a little smaller. So if you see, this is my numerator. So I have to expand this. There is no other way apparently. So this becomes ab, and then I raise it to power 2. It becomes x squared minus 2xy plus y squared. The next one is bc. I expand that one as well, y squared minus 2yz plus z squared, and then I have ca, z squared minus 2zx plus x squared. And now let me multiply it like this. So I will multiply, so I just expand this, yes. So AB x squared minus 2AB xy plus AB y squared. And then the next terms are BC y squared minus 2BC yz plus BC z squared. And then I have ZA CA z squared minus 2CA zx. And then finally CA x squared. But now, instead of this term, so I have these three terms that I was looking for, this one, and this one, and this one. And I can use this expression for the first one, this expression for the second one, and finally this expression for this third one. Yes? So, let us do that. So then it becomes equal to ABX squared. So instead of this, I will put this expression. So it becomes plus A squared x squared plus B squared y squared minus C squared z squared. But after this is finished, I will have this term and that term. So this becomes plus ABY squared plus BCY squared. And then instead of this term, I use this expression. So I would write plus b squared y squared plus c squared z squared minus a squared x squared. And then after this term is finished, I will have these two terms. So let me write them down. So it becomes bcz squared plus caz squared. And then I reach to this term where I use this instead. So this becomes plus a squared x squared plus c squared z squared minus b squared y squared. But then after this term is finished, I have one more term left, which is cax squared. But now look here, there are some terms that can be cancelled. So for example, this minus cz squared, c squared z squared can be cancelled with this one. And then this minus b squared y squared can be cancelled with this positive one. And one of these minus a squared x squared can be cancelled with that one. And then what is left for me, I need to be able to factor something out so that I can see somehow a connection with the denominator if I am supposed to simplify things. If you have this in mind, then it is not that hard to guess what to do. So here, for example, I take this term. My goal is to take b out because I want to make this appear. Okay, so I need to have ax squared. So if I take b out from this, I will have my ax squared. So then I need to look for the term b squared y squared if there is such a term. And then immediately you realize, yes, there is such a term. So between these two I can factor a b, and then you need to find bcz squared. Is there any bcz squared? Yes. So between these three terms, let me not confuse you, let me just factor a b out right now. So this becomes equal to ax squared, and then I will have by squared, and then I will have cz squared. Yes. So between these three terms, I pull the b out. Okay. And now the idea hopefully is clear. So let us go to the next one. Here I will take this one. My goal is to take an a out. So I will take this one. I will take an a out. And then finally I will take this one and I will take an a out from all of them. So then if I take an a out, then it is ax squared plus by squared plus cz squared. Yes, so I consider these three terms and I pull a out. Yes, the good point is that you see that this is exactly the same factor. And then probably everything becomes clear because there is only three terms left. So this one and this one, and there is one more here, this one. So they share a factor of c. Yes, so I can pull a c out. Then what is left, you see from here, if I pull a c out, there is ax squared left, and then if I pull a c out from here, by squared is left, and then finally if I pull c out from here, cz squared is left. And then this gives me an emerging factor common to all of them, so I can pull this expression out finally. Yes, and then what is left is b, a, and c. Yes, so this is my numerator. But this part itself is exactly the denominator. So if I divide my numerator by the expression which is in the denominator, then you see that this term and this term, these expressions are cancelled, so I am left with b plus a plus c. So therefore, the question mark is equal to the numerator divided by the denominator would be exactly a plus b plus c. And that is what is provided by the answer. Okay? Good. Okay, now we go to this problem. Here we have a, b, c be mutually distinct real numbers. So it means that a is not equal to b is not equal to c, and a is also not equal to c. Okay, so they are mutually distinct numbers. We want to show that definitely this number is a non-zero number. Okay, so this is one of those problems that is mainly based on the previous lectures. Yes, so I proved this by contradiction. So I would say that assume that this is not the case. This is not the case, and the third root of a minus b plus the third root of b minus c plus the third root of c minus a is equal to 0. My goal is to show that this is not equal to 0. If you say so, if you say this is equal to 0, I will show that this will give rise to a contradiction. Okay, how we do that? So do you remember we had an identity in one of the lectures about algebraic identities? I told you that if I have something in the box added to something in the triangle, it's three numbers. If the sum of three numbers is equal to 0, we realize that we can conclude that the third power of the first one plus the third power of the second one plus the third power of the last one is equal to 3 times the product of these three expressions. Okay, so that was one of the identities that I proved in one of the lectures related to algebraic identities. Okay, now consider this to be your box. Consider this to be your circle, so consider this to be your box, consider this to be your circle, and consider this to be your triangle. If this is not the case and this sum is equal to 0, based on this expression I can say that the third power of the first one, so let me write it here for you. So we know that the third root of a minus b plus the third root of b minus c plus the third root of c minus a is equal to 0. So according to this identity that I have written in blue, this implies that the first one to power 3 plus the second one to power 3 plus the third one to power 3 is equal to 3 times the first one times the second one and times the third one. Yes, but then what can I write? This implies that the left hand side of this identity can be written as a minus b, because this third root to power 3 I will get a minus b, plus the second one will be b minus c, the last one becomes c minus a, and on the right hand side I can write 3 times the third root of a minus b times b minus c times c minus a. Yes? But now look here, this a and minus a are cancelled, this b and b are cancelled, this c are also cancelled. So this is nothing except 0. So this implies that 3 times this expression is equal to 0. So this means that under the third root sign should be 0. Okay, and now because the product of 3 numbers is equal to 0, this implies that either the first one is 0, which means a is equal to b, or the second one is 0, which means b is equal to c, or the last one is equal to 0, which means that c is equal to a. But this is a contradiction. This is a contradiction. Yes, because if you see, it was mentioned that these 3 numbers are mutually distinct real numbers. So none of them actually can happen. But it tells you that at least one of them should happen. Okay, this is a contradiction since, so let me make it nicer, since A, B, and C were assumed to be mutually distinct real numbers. Okay, so it means that if you don't accept that this cannot be 0, so it means that you have to admit that this is equal to 0, but admitting that this is equal to 0 gives rise to this fact that at least one of these conditions should happen. But this is in contradiction with respect to what we assume about these 3 numbers to be 3 mutually distinct real numbers. Okay, so that is the proof of this problem. Okay, finally the last problem of this problem set. Here a, b, and c are given real numbers with 2 properties. Yes, we know that 2a plus b plus c is equal to 0. We know that ab plus bc plus ca is equal to 0. And we are supposed to find a value or values, possible value or values of this fraction. So in general, you know that we have 2 pieces of information and we have 3 variables a, b, and c. So in general, 2 pieces of information is not enough for solving for 3 unknowns, unless that is a special case, and in this case this is indeed a special case. You will see. So what I do, I start from 2a, from this 2a plus b plus c equal to 0. I add negative a to both sides. You will see why. The left hand side becomes a plus b plus c, and then the right hand side becomes minus a. So I added minus a to both sides. The reason that I did this, because the next step, in the next step I want to raise it to power 2, and then if you remember this identity from my previous lectures, you know that there is an expression like this will appear inside this when I square it. So let me just do it for you. So then it becomes a plus b plus c to power 2, and on the right hand side I will have minus a squared. Yes? So if you remember, this trinomial to power 2 is like this. So you raise the first one to power 2, the second one to power 2, the third one to power 2, and then you write 2 times the first one times the second one, 2 times the first one times the third one, and 2 times the second one times the third one. And on the right hand side you will have a squared. If I move a squared here, it becomes minus a squared, and this will cancel that one. So the left hand side becomes b squared plus c squared, and between these 3 terms I can factor a 2 out. So it becomes AB plus AC plus BC. And on the right hand side, because A2 is cancelled, I have 0. But the good point is that this expression that you see here is exactly this expression here, and this expression is given to be 0. So if I put 0 instead, 2 times 0 is 0. What is left for me is b squared plus c squared on the left hand side, and on the right hand side I will have 0. But this is one of those exceptions that you can solve for two variables here, because now you see that this is non-negative, this is also non-negative. Why? Because this is an even power. So the sum of two non-negative numbers is equal to 0. This happens only if each one of them is 0 individually. So this means b squared is 0 and c squared is also equal to 0. So this implies that b is equal to c is equal to 0. Okay, so we got two of them. And then third one is also very simple, because the sum of these are 0. We know b and c are 0, so b, this is 0, this is also 0, so this means 2a is equal to 0. When 2a is equal to 0, this also means that a itself is equal to 0. Yes? Now that we know a is equal to 0, b and c are also equal to 0, so the question mark that I was looking for is a squared, so it becomes 0 to power 2 divided by 1 divided by b squared, 0 divided by 0 to the power. By the way, as you really see that b squared plus c squared as a combination is 0, so I can also use that fact, so I can just write 0, I can just write 0 plus 1, so this becomes 1 at the end. So the answer to this problem is actually 1. Okay? So if you think that this video was somehow useful, I would appreciate that you can give me a thumb up, and I want you to know that by subscribing to my channel you can support me. Okay, until the next video, thank you and goodbye.